Definitely. I mean, there's obviously a large volume of cell sales with larger systems. But initially, we're starting with the smaller systems, so residential, community systems, but then can scale up to the bigger systems in 1 or 2 years' time. In some vehicles that you see, they're around 140 sort of watt-hours per kilogram. We're already achieving 200 watt-hours per kilogram, and we expect in 2.5 years' time to get to 400 watt-hours per kilogram. And if you do the maths on that, you're reducing you either have the same range of vehicle and reducing the weight by a factor of 3, or instead, which is what's preferable, is that you keep the same weight of battery and your range triples.
Right,
and that's one of the key things that's holding back EVs, is what's called range anxiety.
Absolutely, yeah.
So, a vehicle like the Nissan Leaf has got a range of about 100 miles. But for EVs to take off, you really want to have a very similar range to a petrol or diesel car when you can go 300 miles or more. So that's one key factor holding it back. The other thing is, you want to make sure that you've got safe vehicles. So we've done a number of tests on lithium sulfur. It's intrinsic in the chemistry itself. There's sort of 2 factors that come into play. One, there's what's called a passivation layer, which is a coating that forms over the lithium, which protects the cell. And the second thing is the electrolyte that we use, which has a high flash point to it. And those 2 factors contribute to the safety of the cells. And I always say that sort of the proof is in the pudding. So we've done lots of different tests. We've put nails through our cells. For the military, put bullets through them. There's a range of other tests that we've done, particularly for getting UN 38.3 certification, which is a transportation certification for cells. So we've passed all those tests with flying colours, so it's very promising. Commercialization has started now, so we're working with GP Batteries of Singapore. They're already producing the cells in limited numbers at the moment. That's used very much for sort of prototyping work. So in any introduction of a battery, you have to build prototype batteries and test them and check them within systems. So that's what we're going through at the moment, and then they'll be in sort of commercial use early next year. Any of these new technologies, it's a calculated gamble. So you're looking at the potential of it and you're looking at the reward of it. So, the key thing for lithium sulfur initially is if you look at what the theoretical energy density is, and it's 5 times that of lithium ion, which means if you can achieve that, you've got 1/5 the weight of battery. So that was really the key thing that attracted the initial team to work on lithium sulfur. But then as you start sort of doing more research and getting better results, you understand the other advantages of the technology, just as the safety aspects and a number of other elements. Well, we think that we are ahead of the game in lithium sulfur. There's nobody else out there with cells that certainly have the cycle life and the safety that we have in lithium sulfur. I mean, the key competitor for us is the incumbent, which is lithium ion. So it's to displace lithium ion. There are other technologies on the horizon. So things like people talk about lithium air sometimes, but lithium air generally is being expected to be 2030 or 2040 before that's really available. That's a very difficult one to crack. There's definitely a big space there for a new technology to come along that really addresses the issues that people have in different markets, the EV market, solar market, the defence market. But for us, there are 3 markets that we're starting with. We can see there's a lot more potential in the technology, but you can't do everything at once.